In this video lecture, we are going to discuss about the exponential functions. We are going to talk about the examples and the applications of the exponential functions, and also we're going to see the graph of the exponential functions and the equations of the exponential functions, and we are going to try to solve a couple of problems in the relationship between the equations and the graphs. So I would like to start today's lecture just from the example. So let's say I've got just a sample with one cell inside, and let's assume that the cells are going to split into the two parts every second. And what I would like to do is I would like to track the number of the cells over the time, and I've created this kind of table where I would like to write down the number of the cells over the time. So let's assume at the time 0, I've just got one cell. After 1 second, when the time is equal to the 1, the number of the cells is equal to the 2, and after 1 more second, when the time is equal to the 2, the number of the cells is equal to the 4. So I just would like to continue this table. For example, when the time is equal to the 3, it's going to be equal to the 8 cells. When the time is equal to the 4, the number of the cells is 16, and so on. And I would like to put all of these points, the time versus the number of the cells, into the graph to see what is the connection between these points. So I would like to put the first point, 0 and 1, where the 0 is going to mean the time and the 1 is going to mean the number of the cells at the time 0. So then I can just put all of these points there. So for all of the points, the x coordinates are going to mean the time, and the y coordinates are going to mean the number of the cells. And you see, so the number of the cells over a small amount of the time are increasing a lot, right? And if I would just continue all of this, connect all of these points, I would get this kind of graph, which I'm going to call as an exponential function. So what I would like to do is I would like to try to understand, hey, what is the number of the cells on a certain time? And I can see and figure out the equation of this rule from here. So the cell number at a certain time t, let's say, is going to be 2 in the power of time. So you can see this from these examples, right? So here, if the time would be equal to the 0, then 2 in the power of 0 would be equal to the 1, which is here 1. So if the time would be equal to the 1, then it could be 2 in the power of 1, which is 2, which I can see here, and so on. So if the time would denote the x and the number of the cells would be denoted as the y, then the function, so the equation form of this rule would be y is equal to the 2 in the power of x. So this we call as an exponential function. So one of the applications and examples of the exponential functions in biology would be to track the number of the cells over the time. So we can apply the exponential functions in many different areas. For example, in physics, I would be interested to understand the intensity of the light over the depths of the flow. So let's say I've got a water, and I'm going to flash a light on the surface of this water. And what I would like to try to understand is, I would like to try to understand how the intensity of this light is going to decrease as the light is going through the water. So let's assume that, let's denote the surface to be x is equal to the 0. Then as I go deeper and deeper, for example, x is equal to the 1 or x is equal to the 2, I just would like to try to understand or quantify the intensity of the light. So obviously the light is going to decrease, the intensity of the light is going to decrease a lot, right? And it appears if I would like to try to understand what is exact intensity of the light at every meter, then I could just use so-called B-Lambert law, which is going to have this the exponential form. So you see, so this e in the power of some x, where x is going to mean here the depths. So how depths you are going. Sometimes we call this kind of rules where you're going to have some number in the power of minus x as an exponential decay. So intensity of the light is going to decay exponentially. So another example of the exponential functions is in the probability theory. So one of the most important distributions in the probability theory is called the normal distribution. So we can see the distribution of like a normal. So this distribution is called normal because it reflects many probabilistic models which are going on around us. For example, if I would just get the scores of all the students after some exam, then if I would just like create a histogram of those results, essentially just count, hey, categorize the scores. So, hey, how many students have got just the really good scores, how many students have got the really bad scores, and how many students have got the average score. And the height of this curve is going to mean exactly the frequency. And this can be applied to our example with the exam scores, right? So it's normal to expect that lots of students are going to have the average score. So very few students are going to have the high score, and very few students are going to have the low score. And now in the probability theory, so if I would like to figure out the probability of the event in a certain interval, or for example, if I would like to know the number of the students who scores in a certain interval, then I need to find the area under this curve. So in the probability of this area, in the probability theory, this area is going to be the probability. And in order to find this area, it appears we need to integrate this curve, which is again expressed as an exponential function. So you see, so the exponential function is widely used in so many areas, starting from biology, physics, probability, statistics, computer science, and so on. And understanding the exponential functions are going to help us in the future, so no matter what is going to be your profession. So let's consider the equation, the general form of the equation of the exponential function. So in general, the exponential function is going to be written as a b times a in the power of x plus c. So we are going to call, so this a should be a constant. So b, a, and c are the constants, and x is the variable. So for example, it is possible that your exponential function is given in this way, 1 over 2 times 3 in the power of x plus 4, or 1 over 2 in the power of x. It is okay that this basis is going to be smaller than 1 as well, but it's really important to keep in mind that the basis of an exponential function should be always positive. So there is a good reason for this, because we want that our function is going to be continuous. So you can take any value for the x, including the rational numbers was the denominator, was the even denominators. So if you remember, so the a in the power of 1 over 2 essentially means square root of a, right? So just making this constraint that a is always positive just like enables us to define the exponential functions as the continuous functions. So let's continue. So most of the time, I see the situations where people are mixing up the exponential functions and the power functions. It's really difficult to, it's really easy to confuse these two functions, and I would like to try to understand what are their forms. So the exponential functions are written in the a in the power of x, for example, 2x, and the power functions are written as the x in the power of a, for example, x in the square. So you see, so these two functions are very much similar. So you just, it's easy to make a mistake whenever we're talking about the exponential functions and the power functions. So if you look to their graphs even also look very much similar. So for example, the graph of the exponential function, which is 2 in the power of x, which we have seen before, is going to be like this, and the graph of the power function x squared on the right hand side part of the rectangular coordinate system is going to be like this. So even their graphs are similar, right? So okay, so what can help here to try to understand what are the differences between the power functions and the exponential functions is that, so you need to always keep in mind that the exponential function is the constant in the power of the variable, and the power function is the variable in the power of constant. And graphically, in order to distinguish them, so we need to look to the left-hand sides of this graph. So as you can see, the exponential functions are always increasing functions. So as you are going from the left to the right, the height of the exponential function is always increasing. So as you, for example, can see for the power function, the parabola x squared, so it's decreasing. So here it's decreasing, then it's increasing. Okay, so graphically they're also different, but we need to look to the full graph. So for the negative values of the x and for the positive values of the x. So now let's look to the graph of the exponential functions in more details. So here what we've seen the exponential function before. So we just drawn the 2 to the power of x for the different values of the x. Then when x is equal to the 0, it's going to be equal to the 1. So we've got just this point, right? So essentially 0 and 1. When x is equal to the 1, the value of the function value is going to be equal to the 2. When x is equal to the 2, it's equal to the 4, and so on. So what happens if we just go to the left-hand side? For example, if x is equal to the minus 1, so the y is going to be equal to x in the power of minus 1. So we know that any number in the power of minus 1 is its reciprocal, or just 1 over this number. So the 2 in the power of minus 1 is going to be 1 over 2. So essentially when the x is equal to the minus 1, its value is going to be equal to the 1 over 2. When x is equal to the minus 2, the value of the function is going to be equal to 1 over 4. And when x is equal to the minus 3, its value is going to be equal to the 1 over 8. So let me show you how we can calculate this. So for example, when x is equal to the minus 2, it's going to be 2 to the power of minus 2. And we can write this as 2 in the power of minus 1 in the power of 2. We know that 2 in the power of minus 1 is 1 over 2, and 1 over 2 in the square is going to be 1 over 4, which we have here. So when the x is equal to the minus 3, we can again calculate this as a 1 over 2 in the power of 3, which is going to be 1 over 8. So you see, so as we go to the left, the exponential function is decreasing. As we go to the right, the exponential function is increasing. So in general, when this value of the a is bigger than 1, the exponential function is increasing. So we call the function as increasing when, as we increase the values of the x on the x-axis, the values of the y are also increasing. What happens when this value of the a is still positive but smaller than 1? So it appears when the value of the a is smaller than 1, then the shape of the exponential function is going to be different than this. So let's look to this. So this is our function y is equal to the 2x. What I would like to do is I would like to draw the function 1 over 2 in the power of x. So you see, so 1 over 2 is the value of the base of the exponential function. So if you remember, so this was a in the power of x, right? And this is the value for when a is less than 1. So I would like to calculate this function when x is equal to the minus 3. So let's calculate this. So y is equal to the 1 over 2 in the power of minus 3. So in order to calculate this, what we can do is we can write as 1 over 2 in the power of minus 1 in the power of 3. So we remember this rule of the exponentials where we can just multiply the powers of the two exponential functions. So 1 over 2 in the power of minus 1 is going to be the reciprocal of the 1 over 2, essentially 1 over 1 over 2. Or the reciprocal of the 1 over 2 is going to be equal to the 2 simply. So this is going to be 2 in the power of 3, which is going to be equal to the 8. So we can just calculate all the other points in this way. So I'm just going to put the points to here. So when the x is equal to the minus 3, then the y is equal to the 8. When x is equal to the minus 2, so the y is equal to the 4. So here should be the 4. When x is equal to the minus 1, y is equal to the 2. When x is equal to the 0, it's equal to the y is equal to the 1, right? Essentially, if you just substitute here the 0, it's going to be equal to the 1. Then as the x goes to the more righter, the values of the y are going to decrease. So for example, when x is equal to the 1, the value of the y is going to be equal to 1 over 2 in the power of 1, which is just 1 over 2. as x is equal to the 2, the value of the y is equal to the 1 over 4, then 1 over 8, 1 over 16, and so on. So if I just continue, connect all of these lines, I will get this kind of graph. So you see, so depending on the values of the a, the shape of the exponential function might be a little bit different. So essentially, when a is bigger than 0, we are going to have the increasing function. And whenever we say the increasing function, it's when as we increase the values of the x, the values of the y are also increasing. So when the a is less than 1, so a number between 0 and 1 essentially, the function is going to be decreasing. So essentially, as we increase the values of the x, the values of the y are decreasing. So they are going from the top to the bottom. So this is the most important part to understand the graph of the exponential function. So this problem is a little bit easier. So in a sense that if you're given the equation now, you can figure out what is the graph of the exponential function, at least approximately. So for example, depending on the value of the a, we can know whether the exponential function is increasing or decreasing, right? And the rate of increasing of the exponential function is going to depend on the value of the a. So if a is bigger than 1, as the a is bigger and bigger, it's going to increase faster. So essentially, so the shape of the graph is going to be more steeper. So another problem, reverse problem, whenever you're going to have a graph and find the equation from the graph, it's going to be a little bit difficult. So let's consider 2 examples of such a problem where we are going to find the equation of an exponential function from its graph. So let's say we are given this kind of graph. This is the graph of an exponential function, and I would like to figure out what is the equation of this exponential function. So if you remember, the general form of the exponential function is going to be b times a to the power of x plus c. So I'm going to use the coordinates of these 2 points in order to figure out the values of the 3 constants, a, b, and c. So the first point which you need to always use is the point when the graph of the exponential function is going to intersect with the y-axis, for example. So here it's intersecting at the point x is equal to the 0 and y is equal to the 2. So since this point is lying on the exponential function, if I would just substitute the coordinates of this point into the equation of the exponential function, it should work. So essentially, if I just substitute x to be equal to the 0 and y is equal to the 2 to here, to this equation, the left-hand side should be equal to the right-hand side. So let's substitute this. So essentially, a in the power of 0 is equal to the 1, right? And y is equal to the 2 is essentially is going to mean that a b plus c is equal to the 2. So we can just try to guess the values of the b and c so that their sum is equal to the 2. For example, I can choose that a b is equal to the 2 and c is equal to the 0 so that their sum is equal to the 2. So please note that this function in this form is going to satisfy this point. So essentially, if I just substitute the x and y coordinates of this point into this function, it is going to be true. But at the same time, I can have the shape of this function in this form, a in the power of x plus 1. So again, so the c is equal to the 1, b, which is the coefficient before the a in the power of x, is also 1. The sum is equal to the 2. So this function is also satisfying the coordinates of this point. Essentially, if I just substitute the coordinates of this point, it is going to be true again. So from this point, x is equal to the 0 and y is equal to the 2, we can roughly figure out the form of the exponential function. But we need one more point in order to figure out the form of the exponential function. So, but by the way, please note that the exponential function is increasing. It means that the value of this a should be more than 1. Now let's look to the second point and try to figure out what is going to be the exact shape of this exponential function. So the second point is given as the x is equal to the 1 and y is equal to the 5. So please note that, say, the y is an odd number, right? So what does it mean? So if I just look to this function, So no matter what is the a in the power of x, I'm always going to multiply this to the 2. It means that the values of the y are always going to be the even number. Always. No matter what is the x, the y value is always going to be an even number because I'm going to multiply this always to the 2. So that is why this is not going to be our function. So we need to go for the red one. So in order to find the exact value of the a, I'm just going to substitute the value of the x to here and the value of the y to here and figure out what is the value of the a. So essentially 5 is equal to the a in the power of 1 plus 1. So if the 1 goes to the left hand side, it's going to be 4 is equal to the a in the power of 1. So it means that the a is equal to the 4. So the general form of our exponential function, which corresponds to this graph, is going to be 4 in the power of x plus 1. And you need 2 points in order to find the equations of the exponential function. So let's do one more exercise in a similar way. So we're given the graph of the function and we need to figure out its equation. So again, so the graph is given now in a different form. So it is given in the form of decay, so in decreasing function. So we're again given 2 points. The one point has the coordinates 0 and 0.5. And the second point has the coordinates -1 and 2. And we need to figure out the general equation of the exponential function, which would satisfy these 2 points, or which would correspond to this graph. So essentially, if I just substitute, I need to find the values of the b, a, and c. So again, as we did for the last time, so I'm going to choose this point, an intersection point of the curve with the y-axis, where x is equal to the 0. So if I would just substitute x to be equal to the 0 and y to be equal to the 1 over 2 to the general form of the exponential function, I would just get that the b plus c should be equal to the 1 over 2. So it implies the 2 possible ways of an exponential function. One is going to be 1 over 2 times the a in the power of x, right? Where the value of the b is equal to the 1 over 2 and c is equal to the 0 simply, so that their sum is equal to the 1 over 2. Or there is another way to express this function. Essentially, the value of the b is going to be equal to the 1 here. The value of the c is minus 1 over 2, so that the sum is equal to the 1 over 2 again. So essentially, we are figuring out these 2 curves from this point. So essentially, if you just substitute this point to here and to here, so in both of the cases, that is going to be true. So what we need to now decide is what is the exact form of this exponential function and what is the value of the a. In order to do this, we're going to use the coordinates of the second point. And again, so the coordinates of the second point are given as the x is equal to the -1 and y is equal to the 2. And as we did before, you see, so the value of the y to be equal to the 2 is an even number. And here, in this form, we are never going to get an even number. So essentially, it's like, so we're going to get some integer here, okay? So if, for example, a is and the value of the 2, for example, it's going to be an integer, okay? Then we need to subtract the 1 over 2 from this integer always. So most probably our curve is in this form. So I'm just going to develop our theory that our function is in this form and try to figure out the value of the a. So in order to do this, we're going to use the coordinates of this point. So I'm just going to substitute the coordinates of this point to here and figure out what is the value of the a. So if I would just put this, what I would get is, so the 2 is going to be put here, and -1 is going to be put instead of x. It's going to be equal to the 1 over 2 times the a in the power of -1. So if I just multiply both of the sides to the 2, I could find that the a in the power of -1 is equal to the 4. So that is why a is going to be equal to the 1 over 4. So the general form of this function then is going to be in this way. So the y is equal to the 1 over 2 times 1 over 4 in the power of x. Okay? And essentially this point now is going to satisfy this function, and it's more or less clear that the shape is corresponding to this equation because it's a decreasing function. And if you remember, for the decreasing function, we've got just value of the a less than 1. So this was an introduction to the exponential functions. So we discussed the equations and the graph of the exponential functions and their relationship. In our next videos, we're going to discuss more deeply about the exponential functions and their invertibility and their inverse functions, namely logarithmic functions. Thank you.